I've gone and taken some resistance measurements of some of the precision resistors, or all of them for that matter, and the range switch and the sensitivity switch, and then I checked to see how far out of tolerance they were. I'll tell you quickly, the sensitivity switch they're all good. The worst is out by 0.64%, well within the 1% tolerance by magnitude, requiring no further action. The range switch, on the other hand, is terrible, especially on the 2 meg resistor, out by 22%. The other 2 meg is out by 29%. The 20 meg is out by 1.85, and the lower value ones, this one's by 1%, just barely making it. We could see this one 5.15%, and only one made it within standards is 0.65. So they're all garbage. They need to be replaced. It's not going to be enough to stop from working on this thing and testing it and proceeding along. So I'm going to have to order up these precision resistors right here. Obviously, I don't stock those values in 1% or less. I also decided that if I'm going to order those special resistors, I'm also going to order some polypropylene capacitors to specification to replace these caps here. Because of that, I'm just going to do a simple test on these and keep them in circuit for now. I've completed the measurement of all of the other resistors. It should come as no surprise based on the usage of this device that they did not get beaten up. These are silver within 10%, and all of them, in fact, were. One note, however, is this one right here. It came in at like 8.9%. This one came in at 8%. I'm going to watch those, but I'm not making any changes till I get this off of the variac and onto the isolation transformer, where I could see the normal operating voltage, which will allow me to, again, reevaluate this chart right here. I start with this chart with the factory voltages, what would be expected back in the day, to these values on today's voltages. For the quick testing to be done, I could see here that looking at this particular capacitor and the voltage coming off of it, this side's obviously ground, but this is coming into the pin on the 5879, and we're seeing the correct voltage on that pin. It says that if it is leaking, it's definitely not leaking terribly. We're going to test it anyway. This is just some quick anecdotal evidence to that. This one over here is rated to 200, and it is expected to see 11 volts, or actually 9 volts, through its service. So if this were a leaky cap, even if it were an extremely leaky cap, I could also expect that this one would probably have no impact either, because the voltage is just so absolutely low for its regular service that it would not even affect it. This one over here, this 2 microfarad 200, is a different story, and I'll tell you why. Because that one, which goes to the meter, does provide through resistors a means to ground. And when I go and look at the documentation, and I say to myself, what is that also touching? We find that it is touching the 12AT7 at pin 1, and that goes through a resistor, which granted is a little bit higher, but it is only traceably higher. And when I look at the 12AT7 at pin 1, we see a drop from 85 to 74, which is a considerable drop, given that the resistor barely moved and the input voltages are a little bit higher, right? So it gives a possible indication that capacitor is transferring DC to ground. How are we going to know? We're going to pull it out. We're going to hook it up to the IT11. We're going to see what's going on, and we'll replace it if we have to. All three of the capacitors have been pulled out of circuit, and they've been checked for their capacitance value, and all three of them tested really good, and now they're going to get a leak down test to make sure they're acceptable. For that, it's the same procedure. I've hooked them up to the IT11. This one blasted a 200 with absolutely no issue on paper mica. like a brand new polypropylene cap, and this one sees 11 volts. So this one is definitely good. Again, this one too, all the way up to 200 paper mica, ran like brand new polypropylene capacitor. This one's in a very good condition too. So the only one that seems a little bit tired is the top one, but it'll be sufficient for now. I dare say these two don't even require replacement. I've got all the capacitors soldered back in. I've put the metal covers back on, and while I do not have all of the precision components replaced and at least a couple of the resistors replaced, at least it could be fired up safely on the bench to go through the test and calibration procedure to see if that exercise can be done for functionality checks. The first part of test and calibration has the setting of these two pots here, labeled H and G, to the middle position, and there's a pot over here, F, is to be set fully counterclockwise, so I'm going to do that now. With that completed, it says set range switch to set level. I imagine either set level is fine, and set the sensitivity to 100%. And I realize we're doing this without the calibrated resistors, but we're going through the exercise. Set the level control right here, fully counterclockwise, as I have done. Connect the line cord, power to the outlet. Do not plug it to a DC outlet. Okay, we're not using DC. It mentions not to do so. Turn the power on and see that the pilot light and tube heaters light up. The OA2 should show a faint glow after about 30 seconds. So I will turn it on. I imagine the meter is probably going to bump initially as it warms up. After about 30 seconds, once it starts seeing some there it goes. Meter moved. We'll see it settle back down. A visual inspection shows a faint glow coming from the OA2. So far we have gotten through the first paragraph right here, which is the setup for calibration. I'm adding this section to the movie after the fact because I want to be clear here. The voltmeter calibration in this manual that I've downloaded for the IM-58 calls out pulling the heater voltages, which is in and around 6.3 volts. My particular unit is 6.91. Regardless, it's saying that it should be measured and adjusted directly on the meter, that I should be seeing that actual deflection. In actuality, the meter is RMS, and I should, in fact, not be seeing that value. So what you're going to see in this movie is that I've actually set the meter up to see 6.3 volts, and it's in fact incorrect. And I'm letting you know now that it's incorrect, and I'm making a note of this. And you're going to see that it is wrong throughout the movie. But because I'm not taking actual precise measurements at this time, since the parts have not yet arrived, I'm not overly concerned with the outcome. So now it wants me to set the sensitivity to 30 volts and connect a piece of wire to the hot input binding post. I'll assume they're talking about that one right there, as it's the only input binding post. And then it says connect the other side of that wire to one side of the pilot lamp, whichever size gives an indication of deflection on the meter. Okay, fair enough. So I imagine we're going to be using this as a voltmeter to find out what the voltage is, right? So and now we have a voltage right there. So we're using it as a voltmeter, right? Set the sensitivity switch down to 10 volts. I guess the assumption is once you realize that it's less than 10, you're not going to break the meter. We could turn this down to 10 volts, right? Adjust the voltmeter calibration control to show a 6.3 volt reading on the 10 volt scale. Note if a standard meter of known accuracy is available, it may be used to provide a more exact calibration. So I know that with an accurate meter, the pilot is exactly 6.9 volts. So that's what I'm going to be adjusting the meter to. So now we'll get back there. Here we go. There's 7. There's 6.8. There's halfway between 6.8 and 7. There's 6.9 volts. That takes care of the meter calibration setting. Now we'll start with the next adjustment, which is the balance adjustment. And I will point out that I am using the Feeltech, which is running a 2 kilohertz sine wave into the input right here. And I have set it at 1 volt. It says to use your discretion and set it at least half a volt. And I found 1 volt to be sufficient. We ensure the balance is in the middle. Range switch is at set level. Sensitivity sits at 100. And we will turn the level knob here to 100% deflection, or full scale deflection as it were. I'm going to be sure of parallax here, so it may not match in the camera, but it matches what I'm looking at. So we're now set at 100% level. Now we'll set the range to the 2000, 20,000 position right here, and then we will turn the tuning knob for the lowest deflection. Remembering that we're on the least sensitive position, but we're gonna tune it down. Mind you, the frequency display has not been set yet. We're going to disregard that. So we're tuning this down. And eventually it should bump backwards. There it is. There's the bump right there. And we'll stop right there for a second. Now, potentiometer G is just behind here. It's one of the wire-wound potentiometers, one more pointed towards the outside. And I need to now adjust potentiometer G for the lowest deflection on this meter. So I'm going to go around back. I've got it pretty much in the ballpark, but we're going to watch that. We can see it dropping. Now it's climbing again. So I got it right about there. Now, it also states, obviously, that you're going to get to a point where you can't work with this anymore because it's just not sensitive enough. So we could drop to the 30 position. We could see the 30 position doesn't really do us any good either, right? So I'll go to 10. Yeah. 3. Okay, 3 is good to work with. And we repeat this procedure again. So now I'm going to go with the tuning knob. We can see I'm going to tune it down and see it drop just about there. And then come around back. Attempt not to mess this up. And try and get this lower. Like that. And then just keep working this until I get it as low as possible. So this is as low as I got it. Mind you, this is on the 1% scale, so pretty low indeed. Seems good. We're going to continue on. This is not the end of the balance adjustment. This is only halfway through. So now it says with the sensitivity switch now at 100%, so turn it back to 100. Right, there we go. Turn the tuning control for a minimum meter indication after setting this to the 200, 2000. So set level is where we left it before, right? Now we're 200, 2000. And we're going to have to tune this now for a minimum indication. Obviously on the other side of this. The clear opposite end. So we're going to basically doing the same thing again. We're down there. We have nothing to work with there, so we're going to have to now we're going to have to see what the instruction is to calibrate this portion. This one is done. Same process with the tuning knob, but different trimmer, which I'll show in a second. It's nice and low, in and around what the other one was, just if off by just a little bit at 1%. And I will show what is adjusted and why I cannot adjust this on camera. It's just so twitchy. It's a trimmer cap. And this is what was adjusted down here. We've looked at an earlier movie and have seen you get the plastic tweaker all the way through there, all the way clear through to the other side, and then have to adjust that trimmer capacitor in order to get the lowest possible deflection. Next step is fixing this, and I realize it's going to change because the ranges are not right. This has already been shown to be a fault, but we're going to do it anyway just for going through this in practice and whatnot. So basically what happens is I'm going to pick a known frequency on the function generator that I'll be able to align to this, and then I'm going to bring a maximum dip here, and I'll know I'll be on that frequency. I will loosen this knob, manually turn it into that position, and relock it down. So I have nulled what I believe to be 5 kilohertz, on the dip for tuning, and I'm seeing an indication of just over 2 kilohertz, and this gives me now a position to loosen this knob and bring it up here to the 50 position, which I will do now. And now the knob is adjusted and tightened at 50, so I'm going to bring it back to 2 and get a dip at 2 and see if it's pointing at 20 when I do. Yeah, so it's not perfect. It's in the ballpark. This is not what you would call a calibrated meter by any means, this frequency gauge. But just for fun, let's bring it up to 10 and see what we get. This would also be a great time for pointing out for the changing of frequencies. If I was actually doing something here, you know, which generally would be the case, before touching anything on the input, you would go back to 100, go back to set level, which should bring this back to the full sweep, and then it's safe to actually do stuff on. Because if you start pulling cables and whatnot, this needle is going to peg. I just wanted to point that out right quick. So now I've moved to 10K, and the output of 10K is a little bit lower because that's just how the Feeltech is. So I readjust my level at set level in support of that. So we're back up to 100%. I flip back over to 20, and now I will retune. And I know it should be in and around that 100 mark. Let's see how close we get. Yeah, so there we go. So it is working. And finally, we're just going for 20K to see where that lands. Should be on the 200, in and around. Yeah, close enough, I'd say. So the frequency meter at least gets you in the ballpark, lets you know where you're going. It's expected, obviously, when you're testing an amplifier, you know the input frequency anyway. So this just kind of says you're going in the right direction. I'll note that the next instruction, the hum balance adjustment, specifically requires that the case be put on. I'm not going to argue, so I'm going to put the case on and actually screw it together for this next step. The final step talks about setting up the hum balance, and what it requires is not setting up any source on the input. The input is completely disconnected here, though just out of frame. And this switch right here is set to the 2200, the lowest position. This sensitivity, I'll admit, they talk about bringing it right down to 1%. I don't encourage this. I think that once you figure out what you're doing, you could drill this down to 1% because you could screw this process up as much as you'd like and nothing really is going to happen. But as you feel more comfortable doing this, you could start, you know, drilling this down from perhaps 30 to 10 to whatever, right? And now that this knob is calibrated, you want to bring it to 60 hertz or in and around 50 for the purpose of the accuracy of this knob. And when you get it there, you will see that it climbs. You know, I've just brought it in and around to that area right there. You take yourself a screwdriver, and on the back of the unit is that last potentiometer, and that is the hum balance adjustment. And what we're looking for is the greatest dip for that adjustment. So I'm turning it, and I'm watching it drop, and then I'm watching it climb again, and then I'm just bringing it back. And that's as low as I could get it. And with that, the hum balance is set. It talks about brand new tubes in cathode leakage and readings above 1/10 full scale may drop below that after a few hours of continuous operation. This is not a new tube. Or they may mean, in fact, continuous operation, the unit itself running for a few hours and not being shut off. I can't tell if they're talking about the service of the tube or the unit. So whatever, be that as it may, this concludes test and calibration. The unit is now safe to use. So now we're going to do a practical demonstration of this unit, keeping in mind that those high tolerance resistors have not yet been replaced. However, we can demo its functionality. I have a 15K sine wave coming in on the input right here, just beyond the frame of view. And I have already set up the set level to 100% here. I've already done that. And on the output, I've connected this oscilloscope. And currently, the output is just showing everything because the set level is 100%. It's not in, we're not filtering out the fundamental sine wave yet. And what we're going to do is we're going to get started. So I'm going to flip this over to the 2020, just like that. We can already see it got smaller because, you know, a piece of that filter, that dip, is going to at least have somewhat of an effect on it. And I'm slowly going to bring this up to the 15 frequency. It could be between that 100 and 200. We could watch the sine wave is shrinking as I do that, as it gets nulled out. And we could also watch the needle drop as well. And eventually you get something you really can't work with anymore. You can't even trigger at this point, and we're so low. So what we want to do is we want to increase the sensitivity, which will also increase the decibels of output, so we could see it getting bigger on the screen, as well as up here. And we could see artifacts and garbage appearing in there, which is also what we want. So let me continue tuning this very gently now, and we can see that it dips right about there, right? So I think I could just bring it down to 1% at this point. Oh, I get almost full deflection right there. I don't think I could do that anymore, so I'm going to check the balance. Yeah, well, balance, I could really look at the oscilloscope. I could really bring it in, balancing it out. Probably revisit the tuning again, having done that. Yeah, that looks good enough for this demonstration. So what we're left with is the distortion minus the sine wave, and we're looking at in the 1% being the total deflection, we're seeing 0.11% total harmonic distortion for 15K. So that is how this unit works to measure the total harmonic distortion. To have a better appreciation of the functionality of this unit, I've injected a 10K sawtooth wave, as you could see demonstrated here in the unit. I'll move it over to set level so it's not distorted. And there's a sawtooth wave right here. A sawtooth wave is going to have all sorts of harmonics because it is definitely not a sine wave. And we're going to go through the same process. And given that 10K reads about 0.1% total harmonic distortion, we'll see what the exact same wave does as a sawtooth. And mind you, this is a perfect sawtooth, right? So we're going to move it over, and we can see a little bit of that filtering already. And because this is like perfectly distorted, right, by design, we're going to see some interesting patterns form here as we start breaking this down. And I'm obviously going to have to bring this up a notch or two. I'm not going to be able to go very far. And we can see that I am at, see if I can get, a thing I'm going to point out here, by the way, the Heathkit has a balance knob, which I can use. Now watch, I can even drop it further with that balance knob and bring it down, not much, right? The HP actually has a coarse balance knob. It has another resistor, a coarse and a fine. I don't know the extent of this one. It seems like there could be more play because it doesn't go and come back up. I think maybe the condition is so adverse that there really is nothing this test set could do. I mean, look at the screen. I mean, what could you possibly do with this, right? I just wanted to point that out. But for the purpose of this test, we could say that balance knob probably could have scraped, you know, a little bit off of this. We'll say that the distortion in the 10% range is sitting at about 9% total harmonic distortion for this signal, where the sine wave was 0.1%. Curiosity got the best of me. I already knew that this capacitor was garbage, as we had demonstrated during testing, and what I decided to do was to take this capacitor out of circuit, which means that the meter was not going to work. We knew that it was tied directly to pin 1 on the 12AT7. I'd mentioned in looking at the diagram right here that the 12AT7 was showing 74 volts when it should be 85, even though the resistor was only slightly higher than it should be. In removing the capacitor, the voltage did jump a couple of volts. Not too bad, but noticeable enough to say that there is some leakage there, and it could be pulling down the rest of this circuit. So I've decided that even though I don't have a 2 microfarad capacitor, I do have a 1 microfarad and another 0.5 that I will test to see if I could put in the circuit that's very much like this, used from another Heathkit project. And what I'm going to do is I'm going to replace it, and then I'm going to do another comprehensive check of the voltages to see if they have climbed after that replacement has been done. And obviously this is going to require another calibration of the unit. I just tested this cap as well. This one is absolutely perfect on the lowest setting on the IT11. So I'm going to put this in to bolster the capacitance to at least 1.5. This might not look elegant, but it's a lot better than having that capacitor that was pulling DC essentially to ground and taxing the entire system. We're going to take a reading now on pin 1 and see what we got. I realize it doesn't seem like much on pin 1 of the 12AT7, but jumping from 74 to 75 is a couple of percent increase, given that I'm using the exact same amount of AC input voltage. All of the other ones are redone as well. I realize this diagram is getting a little bit difficult to look at, but what I'm seeing is an almost across the board increase in DC voltages as a result of simply replacing that capacitor. So it definitely was pulling down the DC to some extent. Was it like amazing, crippling pull down of DC on this unit? No, but was it appreciable? Yes, it was. So it's a good thing that that capacitor was removed and replaced. And just to demonstrate the effect that today's work has had on this unit, we're looking at the pilot lamp plugged in again to the input for the voltmeter calibration. And we know that the voltage is 6.91 as it was just recently calibrated. We're on the 10 volt setting, and we could see that it is now sitting over there. I need to redo this calibration once more to get it back into specification with all of the other changes throughout this unit due to the voltage fluctuation from that capacitor swap out. I'm sure everything else will need to be calibrated as well. Although I don't need to turn everything back to 0, everything just needs to be tweaked. The change that was made didn't have any overall effect on the characteristics of the machine. Here we're looking at a 1 kilohertz signal. This time it's 5 volts with a 50 ohm impedance that I've set up going into the unit. And I have tested this as a reference before and after, getting the exact same value of harmonic distortion. Also, I've discovered that there is some drift on this unit. I've found that this stabilizes after it runs for about 10 or 15 minutes and the internal case itself heats up. I could feel that the unit is warm. At that point, it doesn't, when setting it up for the lowest dip, it doesn't change any more the resulting value. That said, however, if I were to leave it alone, even as it's stable, the tuned circuit itself and the balance will drift. So this will move off frequency just because it does. So if I were to walk away for half an hour and this were to move up here, I could retune it and balance it. It would drop back down and the lowest setting would come right back down to this original value right over here. This is going to conclude the video on the harmonic distortion meter. Without the 1% resistors in the range switch, it's going to be difficult to get an actual accurate reading. The demonstration was valid. The calibration was seemingly valid with regard to the dip, but with regard to the actual output that we want to see on the meter, it's all suspect until these specific resistors are in place. The set levels have no resistors in them, so that 100% is good. But once you start turning it off of a set level onto one of these, you really don't know where you're going with certainty. That's got to be addressed. The resistors that were mentioned in this part of the circuit here are in fact highly critical. and those would have to be correct. And it was determined that they were. There were a couple others that I will also replace, and they are going to be done. They're just not going to be done in this video. They're going to be done as part of another video that's to be released. But I have reached out to some folks in the EEV blog and asked them to give me some THD values that they have recorded for their Feeltech, and I'm going to compare this unit and its readings and consistency against my HP 331 Alpha and their values to see what the resulting values are, and take a look at all three of them in a harmonic distortion meter shootout. So stay tuned for that video, and thanks for watching.